Welcome back, and remember our last question. After that, we said we are going to look at question number 5. So here is question number 5 for you. And if we have a look at the information given, they say you've got 3 resistors, R1, R2, R1, R2, and R3 are connected to a battery as shown in the diagram below. The internal resistance there is given as 0.3 ohms. And they say the resistance of R1, R2, that one there, and R3 are equal, meaning that R2 and R3 have the same resistance. And then the resistance of R1 is half of the resistance of R2, all right? So you're not giving the actual values of the resistors here. So they are just telling us that R2 and R3 are equal, and R1 is half of one of them. All right? And then the voltmeter across the battery is given as 9 volts. All right. So let's have a look at what we have here. You see at this point, you have a current going in that direction and the other one going in that direction. If the circuit is, if the switch is closed there, and that one is also closed. So at this point, we've got these 2 resistors that are in parallel. And then the R1 is in series with the combination of those 2 resistors. All right. So the first question they're asking here is, what is the value of the EMF of the battery? And then give the reason for your answer. Okay. If we have a look at what we have here, we've got switch S1 open, switch S2 open. So in other words, there is no current flowing. So if there's no current flowing and you have the voltmeter connected across the terminal of the battery, that reading that you get there is our EMF. So the answer there is that the EMF reading is 9 volts because there is no current. Our switch S1 and S2 are open, therefore the reading that you get. So anytime when the switch is open and you've got the reading across the terminal of the battery, you must know that that reading across the terminal of the battery is your EMF when the switch is open and there's no current flowing. All right? And then the second question says, if only S1 is closed, in other words, if this one is closed, what happens? Let's have a look before we go into a question. If this switch is closed, it means you've got the current flowing through there. All right. The current only flows at this part of the circuit and not through that part because the switch is open. There's still a gap there. All right. So then the ammeter reading is 3 ampere. Then they say you must calculate the resistance of R1. Okay, let's go to our clean page and do the calculation. Number 5.1, we said the answer there was EMF is equals to 9 volts because the switch S1 and S2 are open, implying that there is no current flowing. All right. So 5.2, it is this one that you are looking at, that you must calculate the resistance of R1 when switch S1 is open. Okay. So let's have a look at what we have here. What we have, we've got the current of 3 ampere, and then given the internal resistance, we've got 9 volts, and we are looking for that. Okay, so from the equation EMF is equals to IR plus I small r. So if we try and understand this. We said previously that I big R is our V external, and then I small r is our V lost. Okay, so how much is V external? We don't know because we don't have the value of R. So what we have here is we've got the reading of EMF there. It's 9 volts, which is equals to V external, or I can write it as IR plus the current there is giving us 3 multiplied by the internal resistance, which is 0.3 ohms. And then we get that IR is equals to, or the V external is equals to, we multiply those two, and then the answer that we get there, we take it to this side, and then we subtract it from there, and we get the answer of 8.1 volts. All right. So that is the V external. Okay, this is our V external. And then after that, we go on and say V external is equals to IR. Okay, that is what we're trying to do there. And we can break this into, if we look at the R that we have, if the switch S is open, the external resistance is R1 plus R2, because those are the resistors that are working. So we'll have I into R1 plus R2, all right? And then we just calculated there as 8.1, which is equals to the I, we got it from the information that it is 3 ampere into, remember they said R1 is half of R2, all right? So if R1 is half of R2, so what is the combination of those two? If we take this one as 2 ohm, so this one will be 1 ohm, and then we'll get 3 R, all right? Because that one is half of this one, all right? And then from there, we go on and calculate R and find R as 0.3, 0.9 ohms, 0.9 ohms. And then this is the value of R1, all right? So we've got the value of R1, and therefore we can be able to find the value of R2 and the value of R3, because we know that this is half of R2 and R3, meaning that if we multiply this one by 2, it will give us R2, which is equals to R3, all right? So that is number 5.2, and then we go on to 5.3. 5.3 says both switches S1 and S2 are now closed. Will the resistance of the circuit, how will the resistance of the circuit change? Write down increase, decrease, or is the same. So let's check. If both S1 and S2 are closed, how is the resistance there? This 2 will give us a lower resistance because they are in parallel. And then their combination will be added to that one, making the whole resistance to decrease. If we can put the calculations in there and check whether we are telling the truth, the question is asking about how will the resistance of the circuit change. At the moment, when only one switch was functioning, which is switch S1, remember we had 0.9 there as our resistance, and then when we multiply that by 2, we got our reading of R2, all right? So when when you close all the switch, the total resistance there will be just R, because this is 2R and then that is 2R. And then if we do the calculation there, just to confirm, 1 over R parallel, which is the effective resistance that we have here, is equals to 1 over 2R plus 1 over 2R. And then we have 2 over 2R. So 1 over, R parallel will be equals to 1R, which is what we have there. So if it's 1R and this plus 0.9 ohms, so it is going to give us 1.9 ohm, and then when we add it to 0.3, if we add to 0.3, we get, that's 12, that's 2.2 ohm. That is the total resistance when all the switches are closed. But then if the switch is open here, you have 2R plus 0.9 plus 0.3, which is going to be more than the value that we have there, because of this are in series. If you've got resistors in series, they give you a bigger resistance than resistors in parallel. That's why in our homes, our electric appliances, the sockets on the wall are connected in parallel so that the total resistance in the home becomes lower. All right? So the next question says 5.4. The conducting wire of negligible resistance is connected between P and between N and Q. So we've got a wire that is connected between those points, and they say this wire that we are connecting here has negligible resistance. In other words, we ignore its resistance. We say it doesn't have resistance. And what you must know about current is that where there is no resistance, current will like to flow in there, because there's no difficulty for it to flow. So in other words, when the current gets to this point, it won't go that way or that way. What it will do, it will go that way. It will go from Q to N. It will go in that wire. So what happens if it goes in that wire? The question is asking here, a conducting wire of negligible resistance is connected between point Q and point N, point Q and point N. What effect will this have on the lost volts? All right. So if we go back to the equation, just to check how we calculate lost volts, we have V lost, which is equals to I and small r. All right. So if we have a look at this, and that the current has now an alternative route to take, which is that route, the resistance R, what is going to happen to it? Remember, initially we had that resistor there and that resistor and that one plus internal resistance. And now the current, if it goes in that way, it means the only external resistance that will function is only R1. So the resistance will decrease, because now the current is no more going through R2 and R3, which will give us the total of 2,2, including the internal resistance. It's now going to go through the R1 and the internal resistance. So we only have those two resistors, meaning that the resistance, our external resistance there will decrease. Those two will not function. So if it decreases, what does it mean? The current will increase. Because remember, resistance and the current, according to Ohm's law, they are inversely proportional. And then if R decreases and I increases, the combination of IR will increase. Okay? The combination of IR will increase. So IR, we said IR is our lost volts. So the lost volts will increase. Okay, so I hope that was very much easy to understand. And then we'll go to another question. So the next question that we are going to do, I want us to practice more of this effective resistance so that we understand how to go about solving those problems. We are going to go to question number 9 in those questions that you have there. Question number 9, where you have 3 or 4 resistors, 2 ohm resistor, 4 ohm resistor, 8 ohm resistor, and another 8 ohm resistor. And then we've got internal resistance of 0.8 ohms. And then the potential difference there is given as 12 volts. All right? So let's see what we can do with this one. The first question is asking us to calculate the effective resistance of the circuit. Now, it's not asking us to calculate the effective resistance of parallel. It's asking us to calculate what will be the resistor that we can use. How much resistor can we use to replace all of these resistors that are in this circuit? So, when you have a question like this one, this is how you go about solving the problem. Number one, you must start with parallel resistors. Okay, and then number 2, you will add the combination. You add the combination of parallel resistors to the resistor that is in series. Not forgetting the internal resistance if it is there. So if the internal resistance is there, you don't leave it out because you want how much resistance is there overall. So if we look at our circuit diagram here, I'll try and use different colors so that you can follow what I'm going to explain to you. Okay? We've got the current there, it goes through that resistor. When it gets to that point, it splits. Part of this current goes that way, up to there, and then part of this current goes that way. There's no splitting up to there, and then when it gets there, it goes back to that black color, to the other terminal of the battery. Okay, so if the colors are clear to you on the other side, here we've got the red color, and then here we've got, all right, so I'm using different colors so that you can be able to see which resistors you are going to add first, and then which one are parallel to which one. All right, because most of the time you will think that that is also in parallel with this one. But if you have a look at the color that is going through the 2 resistors, is the same color, meaning that if the same color is going through 2 or more resistors, it means those resistors are in series with each other. And then if you get a different color, it means the resistor that has a different color is in parallel with the other one. Like in this case, you've got green color being parallel to the red. So, but then the 8 ohm resistor and that 8 ohm resistor are in series with each other. And then they are in parallel with that one. So when you calculate, we said you must start first with the resistors that are in parallel before you can go to the ones that are in series and also with the internal resistance. All right, so let's see. 1 over R parallel is equals to 1 over R of 4 ohm plus 1 over R of 8 ohm. Remember, this 8 ohm is in series with another 8 ohm resistor. So we say the 4 resistor is in series with the combination of those two. That is why in our equation there we say the 4 ohm resistor is in parallel with the combination of those two. That's why we're writing it like this. And then we substitute. We said R4 is equals to 4 ohm. No need to put that one. Plus 1 over 8 plus 8. All right. So you've got 1 over 4 plus 1 over 16. All right. So mathematically, our lowest common denominator there is 16, and then you get 4 plus 1, because you know that 4 goes 4 times into 16 multiplied by 1 is 4. 16 into 16 goes once, plus 1 will give us multiply by 1 will give us 1, and then so this will give us 5 over 16. And then remember, we are still talking about 1 over R parallel being equals to 5 over 16. And then we said when you get to this stage, what you do is you turn both sides upside down. You take this one to the top and that one to the bottom. You must also do the same to the top and then to that one to the bottom. So we have R parallel over 1, which is equals to 16 over 5. Okay, so this will give us 3,2 ohm. So that this is the parallel combination. And then remember, the question says you must find the resistance of the whole circuit, not only of the parallel, the effective resistance of the circuit. So after finding the parallel resistors, we'll say R effective or R total is equals to R parallel plus R, let's check, of that 2 ohm plus our internal resistance, which is small r. All right. So the answer here that we got is 3,2 plus 2 ohm plus our internal resistance, which is 0,8. 0,8. And then we puncture this in the calculator, and then the answer that we get is 6 ohm. So this is the effective resistance of the circuit. So that is the effective resistance of parallel combination. And then this one is of the circuit. So we said we start first with the parallel combination or parallel resistors. That is what we have done there. And then after that we add the parallel combination to the resistor that is in series with this combination, and not forgetting the internal resistance. So you add all of them to give you the resistance of the circuit. Okay. Jumping on to the next question, number 9.2. 9.2 says, calculate the reading of, on the ammeter. If we go back to our diagram, there is our ammeter there. So we want to check how much reading will we get on that ammeter. Okay. So it's fairly easy because now we've got much information to use. 9.2. From that equation that we have R is equals to V over I, we know that the R, we've just calculated the R as as 6 ohm from there, because this ammeter is giving us the reading of the whole circuit. So the whole circuit has the resistance of 6 ohm. So we have 6 ohm, which is equals to V, which is given there as 12 volts divided by I. Therefore, our mathematical manipulation there will get I as 2 ampere. All right. So that is fairly easy because the whole work was with number 5, 9.1, where you have to calculate the resistance of the whole circuit. And then from there it becomes easy because now you have the reading there. And then 9.2 says calculate the reading on the voltmeter. So which voltmeter are they talking about? They are referring to this voltmeter here. What is the reading on that voltmeter? All right. So let's check number 9.3. From this equation, we can say V is equals to IR. But which V are we talking about? We are talking about this V that is in parallel. All right? It's equals to IR. That V there. And then the I, let's check. We said the current coming through there is 2 ampere. You've got 2 ampere multiplied by the resistance, which is 3,2. And which resistance is that one? It is this one here, the parallel resistance, multiplied by 3,2. Okay, so what we are doing here, remember this resistors, the combination of those two and that one are in parallel with each other. And then the information that we talked about in one of our handouts, we said if you've got resistors in series, what we know is that the voltmeter reading will be the same. All right? So we are using that information here. So the current passing through the combination of the two, if we put all those three together, we'll have a circuit diagram that looks like this. You'll have the power source there. Okay, I won't write them all. And then our internal resistance. We have the 2 ohm resistor, that is that one. And then we'll have the combination of the 3. And then the ammeter. And then there is our circuit. So this one is the combination of the 8 ohm resistor and that 8 ohm resistor and the 4 ohm resistor that is in parallel with those two. All right? So they give us that resistor. So now we've got these two resistors in series. And then the current passing through this is the same current passing through that. So if we've got the reading there of 2 ampere, we'll also have the same current passing through there because these two resistors are now in series. We've got a series combination now, series circuits. All right. So that is why we are multiplying 2, the one that we got there, by 3,2, which is the combination of the resistors that are in parallel. And then we get the answer there as 6,4 volts. All right. So what do we do with this? Remember, we are looking at what we want is the voltmeter across the 8 ohm resistor. All right. So this 6,4 volts is the potential difference or the voltmeter reading across those three that are in parallel. Those combination of those two and that one. So if we try and dissect it and see what we mean, we've got that 2 ohm resistor, and then we've got the 4 ohm resistor, and we also have the 16 ohm resistor, which is the combination of those two. Okay, and then we've got the ammeter there, and then the internal resistance there. So the reading that we just got here, the 6,4 volts, is the potential difference across those parallel, not across the 8 ohm. Now we are going into the 8 ohm resistor and check how much potential difference is there. All right. So because you know that we have the 8 ohm resistor and the 8 ohm resistor, and what we said is that the parallel circuit is a potential divider from grade 10. Our potential difference is 6,4. So because there are 2 resistors, you divide that by 2. And then this will give you 3,2 volts. All right. So the potential difference across the 8 ohm resistor is 3,2 volts because the parallel resistor is a potential divider. That is why we are dividing the potential difference of the parallel by 2. So this information that you got from grade 10, somehow it will become very useful. Okay, so let us recap. A parallel combination, that is how we go about calculating parallel combination. And don't forget this step where you have to find you swap both sides. You must find, if you want the resistance there, you swap both sides so that you can be able to calculate there. So to find the total resistance of the whole circuit, you add the parallel to the resistor that is in series, and also not forgetting the parallel resistor. And then from there, everything will fall in place. All right. So the next question that we are going to do is question number 10. Question number 10 also deals with, if we have a look at the diagram for question number 10, you've got the 2 ohm resistor, the 9 ohm resistor, the 15 ohm resistor, and the 8 ohm resistor. All right. So you might think that those are in series with each other, but in actual fact, this is in series with the combination of those three. The same way as we had the 2 ohm resistor being in series with the combination of those three. All right. So we also have the internal resistance there. So the first question that they are asking here is calculate the current I. They want us to calculate I. And what do we have? We've got the 12 volts. We've got 12 volts, and then they also give us the resistance. So from the equation number 10.1, from that equation, R is equals to V over I. They want us to calculate I. All right. If they want us to calculate I, we have V. The question is this one, because we've got so many resistors. Which one do we use? So the first thing that we start with is we check, do I have resistors in parallel? Yes, because if I have a look at my circuit diagram here, I'll use different colors again. I've got the current through there, up to there, and then it splits into red and green. The red goes that way, and then the green goes through there. And then when they come together, they form black current to there. All right. So you can see that you've got red being parallel to the combination of those two. So this is similar to question number 9. So let us quickly go through it, because now we know what is it that we must do. All right. So the first thing is to find the parallel resistors. Okay. So to find the parallel resistors, you are going to say 1 over R parallel is equals to 1 over R, let's check, 9 ohm, okay, plus 1 over, I'm making a longer line because I've got those two resistors being in series with each other. So that is R of 15 ohm plus R 8 ohm. All right. And then after that, I substitute 1 over 9 plus 1 over 15 plus 8. So I've got 1 over 9 plus 1 over 15 plus 8 will give me 13. And then from here, you can go straight into the calculator and check whether you can get the same answer. No, sorry, this is not 13. 15 plus 8. Hey, my mathematics is now is 23 there. It's not 13. Okay, so ultimately we'll get R parallel after you do the calculations there, and then you invert both of them. we find R parallel as, if I check here, I have it as 6,47 ohm. All right? And then, remember, this is R parallel. So what do I want? After finding R parallel, I must find R total. All right? So R total is equals to R parallel, the one that I just found, plus R, the one that is in series, which is 2 ohm. 2 ohm plus small r. Okay? So the parallel goes 6,7 plus 2 plus the one that is in, the internal resistance is 0,2 ohm. And then the calculation there will give you, okay, let me put this one aside and not include it. So I get 8,47. Oh, I forgot the 4 there. 8,47 ohm. All right. So you'll see why I didn't include this one, because the equation that I'm going to use, I can include it and then use a different equation and then still get the same answer. We'll see whether we get the same answer. So let's check. We've got the total resistance, and then after that we say E is equals to IR plus, what am I looking for? I am looking for the current, for the I. So I can say I into R plus small r. So you see, this will still have been the same, because this is the R, that is the R, and then the small r is the 0,2. So the E there is giving us how much? As 12 volts, which is equals to I into 8,47 plus 0,2. All right. So ultimately, I find my I to be equals to 1,38. Okay. So this will also be the same if I add that one. Let me check on the calculator. If I add 8,47 plus 8,47 plus 0,2, it gives me 8,67. All right. If I say R is equals to V over I, and R is 8,67, 12 over I, and then I find my I to be 12 divided by 8,67, and the answer that I get is 1,384. So I'll take two decimal place, ampere, which is the same there. All right. So far, so good. And then the next question, number 10.2, how will the reading of the voltmeter be affected if a 9 ohm resistor is removed and replaced with a conducting wire of negligible resistance? So what they are saying is, if we can redraw this circuit diagram that we have here and then remove the 9 ohm resistor and see what happens. Okay, we've got our power source, okay, and then we've got the internal resistance there, and then now this resistor, the 9 ohm resistor that was there, we remove it. We remove this resistor, and then we just put the wire there. We put the wire through there, and then this side, remember, you've got the resistor, which is the 2 ohm resistor, and then 15 ohm resistor. The last resistor there is the 8 ohm resistor. Okay, So this is what we will have when you remove that 9 ohm that was there. Now, I said to you previously that when current flows in a circuit, it wants an easy way to flow. And the easy way to flow is the way that doesn't have resistance. So, meaning when the current flows through this circuit where there's no resistance there, it will go that way. Okay? It won't go to the 15 ohm resistor and the 8 ohm resistor because there's no resistance there. So it will take this part because it's easy for it to flow through there, not through the 15 ohm resistor and the 8 ohm resistor. Now we should ask ourselves, what happens to the resistance, to the total resistance when those doesn't function anymore? Remember, if they were functioning, we had the resistance of 8,67 if we included the internal resistance, 8,47 if we excluded internal resistance. Now, the resistance will jump from 8,47 to this only resistor that we have there, which is the 2 ohm resistor. So in other words, the resistance of the whole circuit, the resistance will decrease because we said those 2 resistors are no more functioning. So you only have this one that is functioning and the internal resistance. So those two will only give you the 2 ohm resistor plus the 0,2, which will give the total of 2,2 resistance. I mean 2,2 ohms. And then those two, the 15 and the 8 ohm, which is 23 ohm, will be out of the circuit. The current won't go in that direction. So you only have the current coming through this part of the circuit. Alright? So R will decrease, and then if R decreases, the current, which is I, will increase. Alright? So R and I are always doing the opposite. If one increases, the other one decreases. So the V external, what will happen to it? Because if we have a look at, okay, let's start with the V lost, which is I small r, we said it will increase. So the V lost, the I and the big R will decrease. Okay, so that is what will happen. And the question, I'm not sure whether we have answered the question. Let's go back to the question. How will the reading on the voltmeter be affected if the 9 ohm resistor is removed and replaced with a conducting wire with negligible resistance? So the answer there, we say it will decrease. The reading of the voltmeter will decrease because the V external has decreased. So the reading on the voltmeter will also decrease. Okay. All right. So we have done justice, I think, to the parallel resistors and calculating effective resistance. And I believe now when you get into the exam room, you will be confident and be able to answer those questions without any difficulty. I just want to have a look at whether we've got another question that we can look at so that we are sure that we are ready. Let us do this one as our last question, question number 11. So question number 11, we have the circuit diagram with resistor M and resistor N parallel to each other, and resistor Y being in series with the combination of those two. So it's similar to the ones that we have seen, the two questions that we have seen, question 9 and 10. And then you've got the internal resistance there, and they are giving us the current there as 2 ampere. All right. So number 11.1, they say you must state Ohm's law. And I said when you state Ohm's law, you go straight to your exam guide, you read and reread and reread Ohm's law so that you know how to state it. It should happen to all the laws that are in the exam guide. The definitions and the laws that are in the exam guide. The actual calculation for the question paper is that with what you have in the exam guide, you've got 40% of this paper, both paper 1 and paper 2 in the exam guide. So if you study the exam guide and you know exactly what is in there, you've got 40% in the pocket. So the other question that they are asking, just to add on the 40%. So stating Ohm's law, we take it from the exam guide, no problem about it. So 11.2, they say, how does the resistance M compare to that of N? Explain your answer. Okay, so how do they compare? If we read the information there, they say the circuit diagram below shows the battery with internal resistance R connected to 3 resistors M, N, and Y. The resistance of N is 2 ohm and the reading on the voltmeter V is 14 ohm. The reading on the ammeter is 2 ohm and the reading on the ammeter A2, which is that one, is 2 ohm. So the reading on A1 is the reading on ammeter A1 is 2 ohm, which is that one, and the reading on ammeter A2, which is this one, is 1 ohm. So quickly, let's check. We've got the current in the circuit, and when it gets here, it splits. Part of this 2 ohm resistor, part of this 2 ohm and 2 ampere, the current of 2 ampere goes through M, and then if that is the case, if the current when it gets to the circuit where it branches, if it divides itself equally, that means that the resistance of the resistors are identical. So how does the reading on M compare to that one of N? The answer there will be the same. It will be the same because the current splits equally between the 2 resistors that are in series, that are in parallel with each other. All right. If the EM of the battery is 17, calculating the internal resistance of the battery. Okay. 11.3 E is equals to IR plus I small r. So what they are asking here is for us to calculate the small r. The E, they give us the E as 17. There, they say if the EMF is 17 is equals to I is how much? Let's check. We said I there is 2 ampere multiplied by R, which is the total resistance which we need to calculate, and time is against us, but the whole calculation there will give you 14. And again, if we have a look at this, we remember that I and capital R is referred to as V external, and V external there we have it there as 14. So we can just substitute it from what we have there, 14 ohm and 14 volts, substitute there plus the current through the internal resistance is 2 by small r. So we will find that small r is equals to or IR is equals to 3 volts, which is our lost volts. So we divide this by 3. No, we divide it by 2, which is the current there, and small r is equals to 1,5 ohm. 1,5 ohm. All right. So that is our internal resistance. And then 11.4, calculate the potential difference across N. The potential difference V at N is equals to IR. So the I through there is 1 ohm, 1 ampere, multiplied by the resistance through the resistance N, which we found it to be 2, and then our answer is 2 volts. So if you have the voltmeter there, it will read 2 volts through N. All right. And then lastly, just to remind you that this section of electric circuits is from grade 11, and it needs you to go back and thoroughly revise it and be sure of what type of questions are coming through there. And the information, you'll get it from the exam guide. From the exam guide, they tell you exactly what is it that you need to know. So go and revise the grade 11 work, electric circuits, and be sure that you can answer all of these questions.